Hi, everyone. Welcome to our virtual road trip webinar series. I'm Molly Soltis with Asphalt Testing Solutions and Engineering, and it's my pleasure to welcome you on board today as we discuss the effects of sample preparation. We're joined by 3 industry experts who will discuss the nuances of sample prep and the importance of establishing consistency nationwide as our states begin to adopt and implement performance testing as part of their acceptance process and specifications. Before I introduce them, let's go over a few housekeeping items. The attendee controls appear at the bottom of your screen. In the bottom left-hand corner, you will find the audio settings. You can adjust your speaker settings here. If you have an issue with your sound, just exit the webinar and rejoin us. Since you are a webinar attendee, you will be in listen-only mode. Later in the webinar, if you would like to join the conversation, you can raise your hand, and the host will unmute you, and you can address our presenters and contribute to the discussion. If you have a question but prefer to stay muted, you can use the Q&A window. Open up the window and type your question, and we will address those questions with time permitting at the end of the webinar. Now I'd like to introduce today's speakers. Tim Webster is the Performance Lab Manager for ATS. He has over 15 years of experience in the industry, 13 of those working with the Florida Department of Transportation, working in material testing. Dr. Jo Sias has been working and conducting research in the asphalt pavement and materials field for over 25 years. She is currently a professor in the Department of Civil and Environmental Engineering at the University of New Hampshire. Dr. Fan Yin is an assistant research professor at the National Center for Asphalt Technology. His research expertise includes balanced mix design, advanced asphalt materials characterization, and sustainable pavement materials. Sorry, Fan. And there he is. All right, and with that, please make sure that your luggage is stowed, your seatbelts are fastened, and tray tables and seat backs are in their upright position. Enjoy your trip.
So hello, everyone. I'm just going to start with a brief overview of some of the work that's been done at UNH and just start with acknowledgements that this work was done under the NCHRP synthesis program. And there's a lot more details in the report, which is Synthesis Report 552. And just quickly acknowledge my co-authors on this project, Dr. Ishan Dawe at UNH, as well as Dr. Leslie Myers McCarthy. And then thank you to our project panel and Ms. Jo-Ellen Gauss, who ran the project through NCHRP. So this, what I'm going to go through is really a result of a combination of a literature review that was done, as well as a survey that was sent out to both state agencies and partner laboratories. And partner laboratories are defined as those labs that support or conduct testing for any kind of state agency. So these can include academic laboratories, consulting laboratories, as well as research arms of state DOT organizations. So that just gives you the context of where this information is coming from. Now, for what we covered in the synthesis, we're really talking about some of the most common performance tests. So these covers some stiffness and viscoelastic characterization, thermal and fatigue cracking tests, rutting, moisture susceptibility, and durability. And again, there's a lot more details on specifically which types of tests we really looked at in the synthesis report itself. So some of the common specimen fabrication variables that we were looking at include sampling location, both production and compaction type, conditioning protocols and specimen age, how specimens are stored and prepared, density or air void content, and then compaction methodology and anisotropy, and then also general information on specimen size and geometry. So we're really talking about fabrication from the point at which the material is produced to the point at which you have a instrumented test specimen that is ready to put into the equipment for testing. Now going into each of these a little bit more, sampling locations, again, various locations where material can be sampled, from at the plant, point of delivery, or behind the paver. And then in terms of what we found for impacts is that you need to really be aware of the potential for segregation in the sampling technique itself. And the literature that's out there shows that there's little to no statistical difference in performance test results due to the sampling location. Okay? But there are differences potentially if there are issues in the sampling process itself. In terms of production and compaction type, any kind of differences in mechanical properties really depend on the mixture type and the lab or plant operations. So various types of mixtures will have differences. Okay? And the characteristics that we're looking at that really impact this are the presence or the amount of recycled materials in the mix, any kind of variable impact from reheating the material, so the process that is used in terms of temperature and time to reheat the material to allow compaction for fabrication of specimens. Okay? And there's not a consistent trend in lab versus field for stiffness or cracking properties. So there's various research projects that have looked at this, and there's really depends on the materials that you're looking at, which have different properties and which direction they're different. Okay. Also, lab versus field air voids can be significantly different, and that can have a substantial impact. Okay. And then finally, when these types of properties are used to predict performance using different payment evaluation tools, okay, the amount of performance or the level of distress that's predicted can be significantly different when those material properties are propagated through the payment evaluation models. In terms of conditioning protocols and specimen age impacts, okay, there are significant differences, okay, that can be measured by the performance test, again, depending on the specific protocols that are used. Okay, so really need to pay attention to reheating, any kind of age conditioning that's done to either to simulate long-term aging or just part of the fabrication process. So temperature, duration, and whether you're looking at the loose mix or the compacted specimen aging matters. It also matters whether you're looking at linear viscoelastic properties or damage properties, and there can be differences in terms of what you're seeing based on what type of property you're measuring. Okay? And then moisture conditioning protocol is also going to have an impact. In terms of shelf life, there's really very little published research that has been done really looking at the impact of shelf life, and what has been done shows no significant effect. Airborne content, this is a big one. Typically, target value or tolerance is specified for airborne content for various performance tests, and some test results may be significantly affected by a small change in airborne content, others are not. So again, it really depends on the range of airborne contents that you're looking at and the property that's being measured. In terms of compaction method, there are impacts in terms of the type of compaction or the mode of compaction, whether it's a gyratory, kneading compactor, slab compactor, and there are differences that have been observed for different equipment manufacturers for the same type of compaction. And one of the things that's key for looking at those compaction methods is that the equipment really needs to be calibrated routinely. And again, in terms of the anisotropy, there's several studies that have looked at this, and there are conflicting results in terms of whether differences in performance properties are measured or not. Specimen geometry and size. Again, there's typically target values and tolerances that are specified for the different performance tests. Precision of stiffness, flow, and fracture properties do tend to be affected by specimen geometry and size, but fatigue properties, there's little to no impact within specific ranges. So again, it really depends on what you're looking at for properties. Just in summary, from the survey results and the case studies, the states are using a wide range of sampling and handling procedures. Okay? And there are some detailed guidance within the states on some aspects. So for example, some states, agencies, or even partner labs have very specific limits on storage time for specimens. Okay? And then other aspects of the specimen fabrication process, there's little to no guidance. Okay? And reheating protocols is one of those where, you know, in a lot of cases, there's no guidance on how this is done from a consistency standpoint. Okay? From the surveys, the most common challenge that both state and partner labs noted was the failure to meet air void or dimensional requirements. And that is something that, you know, some labs have developed a very good procedure for doing this and very good guidance, while others, specifically those that are newer to performance testing, there's more of a challenge with that. And there are strategies that folks have developed for minimizing failures in terms of the specimen fabrication to meet these requirements. Okay? And then the last thing, operator and skill, something that everybody recognized are very important for this whole process. In terms of knowledge gaps and future needs, okay, there is ongoing national research on appropriate conditioning protocols to use. So that is something that is needed. And also in terms of the impact on sampling location and procedures, okay, specifically sampling and splitting, okay, how that is done and what impact, if any, that has on the measured properties. Actually charging gyratory compaction molds, there's various procedures and that are used to do this. And the question is, does that impact what properties are measured or not? Consistently achieving air void targets. I talked about that a second ago. And again, there are strategies that states or laboratories have developed to make this a little bit easier. But there can be some general guidance that's produced for this. Okay, and then there is a question on the necessity for some of those tolerances, or how tight those tolerances are currently in the specifications or in standard practice. And for some tests, you do need a slightly narrower or more restrictive tolerance, and others it might not be as necessary. Okay, and then in terms of the impact of storage times and methods, again, there's some work that's been done on that, but again, there's not a lot of consensus and there's not a large body of knowledge on that to date. Okay, and then again, there is the need for staff training and experience. Okay, with that, thank you for your attention, and I'll turn it over to Fan.
All right, thanks, Joe. Good afternoon, everyone. Thank you for joining us for today's webinar to talk about, the impact of sample preparation. Joe provided a really good, background information about what they learned from the NCHRP synthesis project. I mean, we found here at NCAT, we found that report very helpful. So, help us provide the detailed guidance on how we can prepare specimens, for not only for volumetric mix design, but more performance testing as part of the balanced mix design. So today, like what I'm gonna present is kind of like a few case studies that emphasize the importance in terms of consistency when we make specimens for performance testing and their balanced mix design. Before we get to those case studies, I kind of like want to spend some time to discuss the difference between the volumetric mix design and the balanced mix design. I mean, there's lots of differences in terms of the way we do mix design and production acceptance. But coming back to the focus of today's discussion on the specimen preparation. The first factor that came into my mind when I'm compare volumetric versus balanced mix design is about mix aging. As we all know that when we do the volumetric mix design, pretty much we are looking at the short-term aging, which is, according to Asphalt R30, which is 2 hours at field compaction temperature, which is help us to simulate the short-term aging that happens during plant production, and also to simulate the asphalt absorption that goes into the aggregates. But now if we look at the balanced mix design, aging is a very important part under the BMD framework. I think our industry has reached agreement that, when we do rutting test evaluation, because rutting is early pavement distress, we need to run the test on short-term age specimens. But for cracking, we definitely should consider the impact of asphalt aging on the cracking resistance of the mixtures. So in order to consider the aging impact, it is highly recommended that we run those cracking tests after long-term aging. The next factor that comes into my mind is mix compaction. When we do the volumetric mix design, we always make undesign pills. Depending on which agency we're talking about, the design gyration may differ. But the whole idea is to make undesign pills, and then we measure the bulk specific gravity, and using those information with right specific gravity and some other information, we can determine the air voids, VMA, and some other volumetric properties that we are required to report and use for asphalt mix design approval purposes. But for balanced mix design, because the focus of balanced mix design on performance testing, instead of making specimen to undesign, the common practice is to make specimen to a target height and air voids. For example, when we talk about the ideal CT test, which is one of the most commonly used cracking tests considered by state highway agencies, I think the requirement is a 61 plus minus 1 millimeter in terms of the height of the specimen, and in terms of air void is 7.0% plus minus 0.5. So those are the specification requirement in terms of air voids and the dimension. And finally, it's about the performance testing part. If we look at the SuperPave, the way we are running SuperPave mix design right now, after we finish the gradation, after we determine the optimum binder content, the only performance test we do is TSR, which is a moisture damage test to make sure there's no stripping issue. But with balanced mix design, we definitely put more emphasis on the balanced rutting and the cracking resistance. In order to achieve that, we need to consider like a rutting test, a cracking test, and moisture damage test. So that's going to be like a more effort on the performance testing side as compared to the volumetric mix design. The first case study I want to share information is kind of like about mixed storage. This is a study that we did a couple years ago. When we were trying to look at the impact of aging on the cracking resistance, and the internal discussion we have here at NCAT is like, is there any existing material from existing field project that we can use so that we can establish a correlation to the field performance data? We went back to our inventory of all the loose mixes we have, and then we found out some projects that we think we can use. In terms of the way the mixes has been stored here, they were sealed in 5-gallon buckets with lids on. Okay, I think a few years after we got the sample, those mixes were stored in the storage room with air conditioner. But as we all know that we always run out of a storage room in the lab, and as new materials start to come in, and we have to move the old material to outside storage room. In this case, there's no air conditioner. And here in Auburn, Alabama, in the summertime, it can be really hot. So we got those plant mixes, and we were saying like, okay, let's do the solvent extraction, get the asphalt binder out from those plant mix, and then look at the PT grading of the binder. Luckily we got the same set of data on the extracted binder a few years ago when we did the field project, so that we can compare the PT grading difference before and after like a mixed storage. So here's the results we got. We tested the 5 mixes. Let me see if I can get my pointer working here. So some of the mixes were produced about 6-7 years ago, and they were kind of like on the left side of this picture. But we did find one mix That was from the very first test track research cycle. So that was when we did the study, it was almost 15 years ago. And then for each of the mix I'm showing here, there are two bars, the blue color bar and orange color bar. The blue color bar is extracted high temperature PG grade when we tested during construction or right after construction of those field projects. So that's the data before mixed storage. And the orange bar is after X number years of the storage here at NCAD. When we first got these results, this was really eye-opening for us. We know mixed storage going to have an impact on the property of the binder and the property of the mixture, but we didn't expect the impact to be so this substantial. If we look at the mix 1, which is about 6 years storage, the PG grade changed from 77.9 to 86.3. So that's about 8 or 9 degree increase. But if we look at the mix on the very right side of the plots, this is the data I mentioned, from the first test track research that we have been keeping this mix in the storage room for almost 15 years. And if you look at this difference, I mean, that's almost like a 31, 32 degree on the high temperature end on the extracted binder. So this is kind of like a highlights important that, we definitely need to pay attention on the storage of the mix. One lesson that we learned here from NCAD by looking at this data is that, if we just have the result, if we have the loose mix in the lab, that does not mean that we can use this loose mix for some additional performance testing. We have to do some quick check to make sure like the property of the binder or the mixture has not been changed significantly just because of mixed storage. Okay, I think the data definitely highlights the difference of that impact. The next case study I want to share is kind of like looking to the impact of mixing procedure. Like if we got some loose mix, raw materials and we need to make lab mix, lab compacted specimens for performance testing. What kind of mixing procedure we need to use, to prepare the aggregates, to preheat the asphalt binder, and also preheat the wrap. So on this slide, I showed like a 2 method that we look into kind of like a small study that we did in the lab. The first method is kind of like the common practice that NCAD we have been following. In this case, the aggregate was heated overnight at like a 360, 370 degree Fahrenheit. Asphalt binder was heated at a 315 based on the PG grade of the virgin binder used in the mix. And then for wrap, our common practice here is just to do like a 2 to 3 hours at 275. Okay, we don't want to overheat or overburn the wrap material because we definitely don't want to overage the asphalt binder in the wrap. And also in this small study, we look at a different method based on the recommendation from a contractor that worked with us. For their approach, they look at aggregate heating at a 320 overnight, which is kind of like a 40 degree lower as compared to the temperature we were using. For asphalt binder, it's pretty consistent with what we're using, 320, a little bit over 2 hours. But the main difference here is how we handle the wrap. Their recommendation was using a much higher temperature, but at a much shorter time. So instead of doing 2 to 3 hours at 275 degree Fahrenheit, they were using 15 minutes at 320 degree Fahrenheit. So we got 2 mixes, and for each of the mix, we make the specimens using those 2 methods. And then we ran the ideal CT on the specimens that prepared. And here's the results we got. There are 2 mixes, as I mentioned. For the first mix, the method 2 give us a higher CT index number. The difference may be like a 20, 27, 25%. If we just look at the average number, if we consider the variability of the test result, the difference may not be statistically significant. But if we look at the other mix that we tested, we saw a much substantial difference. In this case, it's almost like a 50, 55% difference. We didn't run statistical analysis on that, but just based on the error bar, they are not overlapping. So I mean, I would expect those results will be statistically significant. So the reason I want to show this result is not, saying like we should trick the system to, play with different mixing procedure to get better results. The whole point I want to make here is that we definitely need to be consistent in terms of mixing procedure, because if we use different mixing procedure, even if we have the same materials, we can have different test results, for balanced mix design. Which could be a concern for, not only for highway agencies, but also for our industry. And finally, I want to share a case study about the Roundrobin study that we did a couple of years ago. The whole idea was to look into the variability of different mixture performance tests that has been used in balanced mix design. We included ideal CT and iFit for cracking, Hamburg and APA for rutting. Here's the mix information. Nothing special I want to mention here. It's kind of like this is a mix with balanced rutting and cracking resistance. So we don't have extreme mix conditions to look into the round-robin study. So the round-robin study we did in 2 phases. The first phase is NCAT provided the planned loose mix. And also we provide a very detailed step-by-step instructions for specimen fabrication. And then we send those out to the lab participant in the study, and we ask them to prepare specimens and run the test and report the results back to us. After the completion of phase 1 study, we look into a second phase, where here in the second phase, we provided the ready to test ideal CT and iFit specimens. So instead of sending loose mix out, our technician prepared all the specimens here following a very consistent procedure. And then we send out the specimens to the lab for testing. So if we compare those 2 phases, in terms of between lab variability in the final test result, for phase 1, the variability comes from the mixed sampling, come from mixed sample preparation, and also come from performance testing. But if we look at the phase 2, because all the specimens were fabricated here, by the same technician at NCAT, we were able to exclude the variability contributed by the sample preparation, okay? So in phase 2 data, we can only, we can look at the variability from mixed sampling and performance testing. So here's kind of like the ideal CT data we got based on all the results we collected. We did a calculation on the between lab reproducibility estimate. And these are the 2 numbers we got for the coefficient of variation. For the phase 1 study, the COV number was 35.3% for ideal CT. But if we look at the number we got for phase 2, which is 20%. So if we compare those numbers, the additional 15% variability was attributed to the sample preparation. So this definitely highlights the importance of sample preparation on the performance test result. So with that, that's all I have for this short presentation. Like I said, this is kind of like just want to provide some quick case studies so that we can look at the real data to see that, sample preparation is important for, balanced mix design. With that, I'm going to turn it back to team.
Alrighty, we want to thank you both, Ann and Joe, for your studies that you showed us today and the information you provided. I wanted to ask a question to Fan in regards to your case study too. The question we kind of had, you're not saying one method is better than the other. You're just saying if you're going to run a set of tests with others, make sure you're using a consistent procedure. Correct? Is that what you basically were telling us all?
Yeah, that is correct, team. I know, when I first got this data, I was thinking oh, does that mean A procedure can always provide a better result than the B procedure? But that's not the the message that we want to send out to our community. The whole idea is that we definitely need to be consistent, especially for state highway agencies that are interested in implementing balanced mix design. I know right now many state DOTs, they are doing the performance testing in-house in their central lab, but eventually, we want all the contractors or consulting lab to be part of this effort so that they can all do the test. If that's the case, we definitely need to be consistent about the way we make specimens so that when we get the results from A lab versus B lab, we know like, we have faith in those results and we can make a connection to the mix quality. That's the most important part.
Okay. I know we're doing some stuff down here in Florida with ideal testing, and that's one of the things that we've had big discussions about, is just trying to make sure everybody's doing the exact same thing. And it's tough because, I can tell you that I am, but I don't know for a fact because I'm not sitting there watching you. So we can be doing things just a little bit different and not even realize it. Let me ask a question. When we talked a little bit earlier, I'd asked this question and you guys really weren't sure, but I'm going to go ahead and throw it out there because it's something we're dealing with right now. We've been using some additives that, as they disperse differently in the mix, they're sealing the sides of the sample along the surface of the mold when we run them in a gyratory compactor. So our fear is that we're getting false air void results because we've sealed up the outside, but yet the tops aren't sealed. And as we all know, much of the focus for air void or for performance testing is air void content. Are there any suggestions that you guys have for us to be able to make it a sample with the correct air void and not have to worry about something like this?
Yeah, so that's a tricky question in terms of a practical solution to that. It's not something that we've run into, but I do understand that it's something that's potentially a real issue, especially with some particular additives. I think one way to tackle it is depending on how those additives adjust the bulk specific gravities or max gravities of the mix. You might be able to use some kind of correspondence with a mix that doesn't have the additive, kind of as a substitute for it. It's not going to get you the exact number,
right?
But if you've got the same volume and you're targeting a height, and you got the same weight in the material, as long as your GMMs are the same, then theoretically you've got the same GMB. So you can do that. The other thing that is a possibility is looking at alternative density measurements. So something like a dielectric constant measurement is an option that doesn't require those measurements submerged or SSD measurements where the sealing's an issue. But again, that's something that folks are starting to look at, but it's not a standardized procedure at this point. So
yeah, like I think I had mentioned earlier, we had a control mix. We got a 4% air void. We then added this, this additive to it and had some polymer dispersion stuff going on. Same weights and everything, thinking, hey, this is going to be great. We're on our way to having some great testing results. And the next thing you know, your air void's 1.7 and 1.8, and you're like, oh my goodness. And we got to make, now we have to make ideal pills, and we're trying to figure out, well, what do we do? Just assume everything's going to be 1% or 2% off. And it was just kind of one of those bing moments, and you're just like, what do I do now? I know I asked Tanya, and Tanya's like, I'm not really sure. I haven't ever had to deal with this before. She goes, make sure you ask Fan and Joe. We'll try to figure it out. So that's why we want to throw it out there. And anybody out there that may have dealt with this problem before, if you have some answers or some ideas, please let us know. We'd appreciate it.
Yeah, team, one quick comment I would like to add is, in terms of, the additives, I did ask our engineers here at NCAT in the lab, since they have more, hands-on experience working with the mix every day. And they told me that we haven't run into, the similar issue that you just described about the additives. But we did run into some of the additives that provide kind of like a compaction aid benefit. So, you can have like a 4% air void on the control mix, and after adding your additive, it helped compaction. Warm mix asphalt is definitely one of those materials. But also, I think some of the rejuvenators or recycling agents that we have been, looking into, the high wrap or high shingle materials, because of softening impact on the asphalt binder viscosity, it can provide, a little bit compaction aid benefit, but not kind of like the additive that you described that they kind of like a squeeze out to the side.
Yeah.
I think the only case cases that we ran into with, asphalt binder on the side of the specimen is when we do BMD modification, we try to put more asphalt binder into the mix to improve like durability or cracking resistance. And then there's only that much room in the specimen. And then if you just keep,
Right.
keep compacting, the asphalt binder going to come out to the side. So,
Exactly.
so yeah.
All right, well, let me see. We've got a question on here. Let me run it by you guys. Fan, in your case study 3, was the time between plant production and sample fabrication consistent for both phases? Do you think this has any contribution to the difference in COV?
I saw the question came from Tanya. So that's a good question. I think the kind of like the short answer to your question is like, no, they are not consistent. Because when we first started the Roundrobin study, we were only planning to do the phase 1 study, which means, we send out the loose mix and ask the lab to make the specimen and send us back. And I think it was not until like, 9 or 10 months later, we realized we still have some additional loose mix available and funding available so that we can do the phase 2. So there's kind of like, the 9 months or 10 months, time delay between, the phase 1 and phase 2. In terms of results, the difference in the result, I would think that the storage, the 9-month storage may have impact on the CT index number or IFIT number in terms of average result, but I really don't know how much it would affect, the variability. But I don't have the data to back up my, expectation. This is the data we got, so that's the data we are sharing with our community.
Okay. All right. Another question I have here says, some samples are tested immediately when others might take weeks to test. How does the mixture respond when allowing the sample more or less time to sit? Does the time start from the point the sample is fabricated or from the point in which it is, say, plant produced?
Yeah, so I think that, some of that, I guess it depends on kind of the relative time that you're talking about. So for example, in some of the data that Ben showed, those really long storage times, even just on the loose mix, can be substantial in terms of the differences in what's measured. There's been a little bit of work that's been done on, shorter, more, what I would say, more typical storage times and shelf times. But again, I don't think that's one of those things that I don't think we really have a good handle on. I do know that just anecdotally and based on experience that once you compact a specimen, it's not, you're going to slow down that aging process. And, especially if it's a type of specimen where then you're going to be cutting and coring, then you don't cut and core until you're ready to test, because then you've got kind of that sacrificial layer on the outside that you're cutting and coring away. But other than that, I don't think there's a whole lot we totally understand in terms of giving guidance on what you should or shouldn't do, other than if you're comparing with other results, you want to make sure that you've got that consistency. And just based on my experience, I think any kind of differences that you might observe are going to be very dependent on the mix itself. So whether you've got recycled materials, a soft binder, a harder binder, an absorptive aggregate or not, I think all of those are going to have an impact. But again, the level of impact and the magnitude of impact, I think we really don't know. So in the absence of that, consistency is really the key.
Okay.
Yeah, I agree with you, Joe, on that. We know that it's important, but really we don't have a whole lot of data to show the impact. Here at NCAT, I think our practice is to start the clock, after the specimens are made, especially for plant mix. Primarily because we don't have the control of when the mix was produced at the plant, right? Typically our clients or the people we work with, they send us loose mix saying like, oh, can you run the test on these for us? So we don't have the control on the actual production date. What we can control is after, like Joe said, after we make the specimens, we try to be consistent in terms of the testing time. At least for a single project, within the single project, we want to be consistent. Maybe like 2 weeks is a time window that makes sure like all the specimens we made should be tested within 2 weeks. I mean, we don't have any data to show like if we just make the specimens, put on the counter, and then let it sit for like, I don't know, 2 months, and what kind of impact it has on those stiffness or modulus or fracture properties. We don't have that data, but I think that'll be interesting. I mean, maybe some of the folks online with us today, they have some data, and they can share with us. I don't know.
We have done a lot of ideal testing lately, and I know we were told initially that, or we were told at some point that try to get it tested within 2 hours of being compacted, or all this kind of and all that kind of stuff. And we had some that we did that way. We had some that sat there for a couple of days, maybe even a week or longer, and it really didn't. On that particular project or whatever, it didn't really seem to make a big difference. We were getting numbers that were pretty consistent overall, and we just were curious if anybody else had any more information and other issues with it that maybe we weren't aware of. So that's why we wanted to throw it out there. We got a couple other questions. Let me see what we got here. One question: did you do any same mix within lab variation studies for the different tests that you ran?
Oh, I assume this is related to one of the case studies I mentioned, or maybe the round-robin study. For that round-robin study, we did look at 4 different performance tests, I believe, like a two cracking test. I showed the ideal CT result, but also we look into the iFit. I don't have the numbers in front of me, but if I remember correctly, the COV, the within lab or the between lab coefficient of variation for the iFit is a little bit higher than the ideal CT. I think like for ideal CT, it was kind of like in the 20% in that neighborhood. But for iFit, I think we saw numbers somewhere between like 25 to 30, 35. I think that is consistent with some other number that has been reported by other researchers. I think there's some reason that kind of like explains why we saw the difference between ideal CT and iFit. So as we all know, iFit, requires a little bit more specimen fabrication effort, right? Like, I saw, team was laughing there. So you make the gyratory, you have to cut in SCB sample, and then you need to cut the notch. So kind of like every single step, there's some requirement on the dimensions, as Joe mentioned in her NCHRP synthesis project. So every single step may have an impact or may contribute to the overall variability of the results. So I think that may be a factor. The other 2 tests we look into is Hamburg and APA, kind of like on the writing side, but I don't have the number and I don't remember. But if you're interested in those numbers, feel free to email me after the call. I'll be glad to share those information.
Yeah, the iFit for sure. I mean, like you said, you're making a big pill and you're cutting it in half, and you're cutting that in half, and then you're trying to add a notch. And every time you do something, you're thinking, okay, this could mess the whole test up. Yeah, so you're exactly right there. All right, let me see. We got a couple more questions on here. Let's see what we got. Okay, fabricated pills, 7/8 inches height, if left standing, could consolidate under its own weight. The density distribution changes accordingly. So do air void distributions. Is that a question or a comment? Not even really sure, to be honest. More of a comment, I guess. All right, so I got another one on here. It says, has there been any studies as to the aging of the compacted specimen versus the loose material?
So yes, there are. There have been NCHRP studies. The most recent was the 954 work on the aging, and they specifically looked at compacted versus loose material. and there are differences, because if you're aging a compacted specimen, you've got aging gradients that are created within the specimen. Again, not a big deal if you're doing things consistently, but you do have to recognize that if you do age using that method, you're not aging a material with a consistent property across its cross section, no matter what way you're testing it. The other thing to consider with that, compacted specimen aging, is that when we're talking about different types of tests, you've got those different specimen geometries, so you're going to have different aging gradients for those different geometries. So it's, something else that you've got to think about in terms of variability in your results. So I think that's what, most of the industry is moving towards aging the loose mix and then compacting, so that you do have a consistent material that you're testing.
And also, like, I guess on aging part, I know, like, our industry, like Joe said, our industry has, kind of like leaning towards using loose mix, try to, prevent those aging gradient issue. But right now, like the Asphalt standard long-term aging procedure is still like a 5 days at 85C. I really don't know how many like agencies out there, or research institute, or or contractors are looking at that aging procedure. As far as I remember, I think Louisiana probably is the only state, since the way they look at the SEB test is to do 5 days 85C aging first and then run the test. And also, in addition to the 954 study, when I was in Texas working on my graduate degrees, and we did the 952 study to look into what, the title is called short-term aging, but we did spend quite a bit of effort to look at the 5 days 85C on compacted specimen. In addition to the aging gradient issue discussed before, the other issue we found out is that, that aging procedure is really not severe enough. Even though we were targeting to simulate, I don't know, like a 7 to 10 years of field aging, but, based on the research we did, we found out that was not the case. It could maybe only simulate like a 2 years or 3 years at the most. If that's the case, it does not give us the opportunity to look into the long-term performance of the properties of the asphalt mixture that we produce. So that's kind of like a little bit additional, information about the question about aging, I guess.
Okay. Tanya, I have a raised hand. Tanya Nash.
So, hello again. In general, I have a question for both of you guys. And first, for Joe, for your survey, as you were starting to look at the differences between how people are storing, what the requirements are in their specifications, maybe possibly with the specifics and the test methods. What do you guys foresee the future steps being for sample prep? Do you foresee them being tighter within the actual test methods themselves? Or do you feel like the states also need to come back with a very specific protocol as we head down the balanced mix design, or even, testing these performance tests during production as we're comparing with the state and the contractors' results moving forward? So is it one-sided, or do you foresee it being a lot tighter, a lot more specific in both the method and the spec?
Yeah, I mean, right now they are honestly all over the place. If you take a look at the synthesis report, you'll see the range and what is reported for those that actually kept track of it. So not only is there a range for folks that actually keep track of it, there's a lot of folks that don't even keep track of that. So I think the first step is kind of a better understanding of what matters and what doesn't. And then once we have a better understanding of what matters and what doesn't, then we need to kind of move towards, well, is it something that's more general guidance in terms of specimen fabrication process generally for performance tests, or there might be cases where some specific tests might be very sensitive to certain certain parameters or certain procedures or changes in certain procedures where that specific test specification might have something additional. So that's just kind of my gut based on what I see and based on my experience in terms of where you see some of those differences, where I kind of envision where we might end up. But again, it's going to end up being something, when it comes down to it, especially when you're looking at mixed design approvals and you get into the acceptance territory, everybody's going to be doing the same thing. Otherwise, there's a lot of opening there for issues.
Thank you.
You got anything you want to add to that, Fan?
No, I mean, I agree with what Joe said. I mean, we know it's importance, and right now we don't have a consistent procedure like nationally or even within the state, right? I know I think a ruggedness evaluation about sample preparation is important. I know there's some ongoing research effort to look into the ruggedness of the test procedure. Like, for example, we talk about the iFit, in terms of notch, dimensions. But I'm thinking like maybe there's a need to look into the ruggedness evaluation of the sample preparation itself. So that, like Joe said, we need to understand what matters, what does not matter. And then like in terms of implementation, I mean, I think, in order to make it practical, I think at least we probably need to start from the state level that, agencies may need to step in and saying like, okay, this is a procedure that we want to use, for, the pilot project you guys are doing or some other research so that we can be, at least consistent. And then like over time, as, new information comes in to tell us what matters, what does not matter, we can make a, revisement and make it better. But, I think bottom line is the key is consistency. So that we can compare results. I mean, if that's something we cannot address, I really don't know like, what kind of impact it will have on those performance tests and also, the implementation of balanced mix design. So.
Okay. Okay. I'm going to back over to Molly and she will close us out.
Thank you, guys. Oops, sorry about that. We're reaching the top of the hour, so we're going to wrap things up. So thank you, Tim, Fan, Joe, for leading such a great discussion, sharing your expertise and your experience. Our next trip departs December 16th. We're going to be discussing asphalt mix performance, and we're headed down to the Louisiana Bayou. So I hope you can all join us then. Have a great day.
Thank you. Bye.
Bye all. Thank you.